This is video lesson number 10. We're looking at bringing things together from the last few lessons and working all the way from a word equation to a balanced reaction equation. So we have a little bit of a review to start with, and then we'll get into some practice questions. So steps to follow when you're trying to do a balanced reaction equation from a word equation is the first thing you want to do is write out the skeleton equation. So you want to figure out what each of the element or compound formulas are, and then balance it afterwards. So skeleton equation, okay, by replacing the name with the correct formula. Then the second step is to balance the equation. Now you may find that if you have a really hard time balancing, that the problem is that you've actually made a mistake in your formula. So if you try to balance and you keep trying and it's just really not working out, chances are that you've probably made a little mistake in writing actual formulas. So double check them and see if you can find where you may have gone wrong. A quick reminder for the naming rules. So for ionic compounds, okay, you're going to write the ions, okay, and use the crisscross method. So for example, if we look at something like magnesium chloride, remember that we take the ions, so Mg2 plus and Cl minus. We use the crisscross method, and that will give us MgCl2 as the formula. But for molecular compounds, okay, we use the prefix, so the Greek prefixes, okay, to represent the number of atoms of that element. So there's no crisscrossing happening. We just say if it's carbon dioxide, then it's 1 carbon and 2 oxygen. So the dioxide, the 2 stays with the oxygen. There's no swapping. So let's jump into a couple of examples. Example number 1. Write the balanced chemical equation for the reaction and state the type of chemical reaction. We've got magnesium bicarbonate breaking down into magnesium carbonate, carbon dioxide, and water. So before we write our skeleton equation, I'm going to go over a quick reminder on how to write each of those formulas. So magnesium bicarbonate, magnesium is a metal, meaning that it's an ionic compound. So we use the crisscross method, so Mg2 plus. Bicarbonate is a polyatomic ion, so it's HCO3 1 minus. Bicarbonate is also called hydrogen carbonate. Because it's ionic, we crisscross, that's going to give us Mg HCO3 in brackets with a 2. Our other pieces here, we've got magnesium carbonate, carbon dioxide, and water. So magnesium carbonate, again, magnesium is a metal, which means we're using the crisscross method. So Mg2 plus. Carbonate is a polyatomic ion, CO3 2 minus. Crisscross, 2 and 2 is a 2 to 2 ratio, so we reduce it to 1 to 1, which is going to give us MgCO3. Carbon dioxide, carbon and oxygen are both nonmetals, so this compound is molecular. The di stays with the oxygen to give us CO2, and then water we know is H2O, dihydrogen monoxide. So now we need to write out the skeleton equation and then balance it. So we've got Mg HCO3 2. So there's our magnesium bicarbonate. breaking into magnesium carbonate plus carbon dioxide plus water. Now we need to check and see if it's balanced, and if not, balance it. In this case, we've got one magnesium, so that one's good. We have the 2 here, remember, applies to everything inside the brackets. So we actually have 2 hydrogens, and over here we have 2 hydrogens. We have 2 carbons. Here we have 1, 2 carbons. And then we have 6 oxygens. Here we have 3, 4, 5, 6. So this one is already balanced. And the type of reaction, because we only have one reactant breaking into multiple pieces, is decomposition. Moving on to example number 2. For this one, we have calcium chloride and sodium sulfate forming calcium sulfate and sodium chloride. So let's figure out what all of these things formulas are, write out the skeleton equation. So calcium chloride, calcium is a metal, which means it's ionic, and we're going to use the crisscross method. So calcium has a charge of 2+, chlorine is 1-, crisscross your numbers, we get CaCl2. Sodium sulfide, sodium is a metal, therefore it's ionic, therefore we use the crisscross method. So Na+, and sulfide is S2-, crisscross gives us Na2S. Our products here, we've got calcium sulfide, so Ca2+, S2-, crisscross 2 to 2 means it's a 1-to-1 ratio, so we reduce all the way to Cas. And sodium chloride is Na+, Cl-, 1-to-1, so NaCl. So let's write out the entire skeleton equation. CaCl2 plus N2S are our reactants. And then CaS and NaCl are the products. To balance this, we have 1 calcium and 1 calcium. We have 2 chlorines, but only 1 chlorine. So we add a 2 in front. That gives us 2, oh, whoops. This should be Na, not just N. Na2, there we go. 2 Nas, 1 S, and 1 S. So now that one is balanced. The type of reaction here, we have a compound reacting with another compound where we're getting a switch of the cation. So this is double displacement. All right, we're going to do a couple other examples. So when you see elements on their own in an equation, we've talked about this briefly in some previous lessons, but we haven't really written it down anywhere. So there's no charge on an element on its own, okay? It's not an ion. It's just a neutral element as it is, okay? So the pure element is being used in the reaction. So for example, if it says copper, okay, in the word equation, then you would write it as just Cu in the skeleton equation. Okay, it doesn't get any numbers, it doesn't get any charges, it's just the element symbol as it is. Now the exception to this rule is the Hofbrinkel gases, or the diatomic gases, which we've sort of touched on a little bit. Okay, and these are composed of 2 atoms, so di meaning 2, atomic, so 2 atoms, okay, of the same element. Okay, these elements are the ones that this rule applies to: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Okay, and so when you have these, any of these written in your word equation, you would represent it in the skeleton equation as whatever the symbol is, so Cl or N, but you would have a subscript 2, okay, because it's two atoms that are stuck together. And that's how the element exists when it's in a pure form. So Hofbrinkel is kind of a quick way that we can use to remember. So it has the symbols. It's pronounced Hofbrinkel with like a K sound instead of like a Cl. We've got hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So those are the ones that this rule applies to, but that is it. No other element gets the 2. Everything else, so all your metals and stuff, are gonna just be written normally as is. So let's do a practice equation with one of those in it. So here we've got iron and oxygen forming iron 3 oxide. So iron is just Fe, so it's a pure element. It's a metal, so it's just like the Cu, it's just like that, Fe. Oxygen, however, comes as O2 because it's part of the Hofbrinkel group of diatomic gases. Then iron 3 oxide, this is a compound. It's ionic, so we have the Roman numerals to tell us what the charge on the iron is. We crisscross, show that step. So Fe3 plus O2 minus, crisscross gives us Fe2O3. So now we can balance this and write out the skeleton equation. Fe plus O2 makes Fe2O3. We have 2 oxygens here and 3 oxygens here. So the only way to balance 2 and 3 is to make them both 6. So I'm going to put a 2 in front of there and a 3 in front of there. So I have 6 oxygens now on both sides. That gives me a total of 4 irons on the product side. So I'm going to add a 4 in front for the reactant side. So there's our balanced reaction equation. The type, we're making a single product, which means that this is a synthesis reaction. All right, we're going to do one more together. So in this reaction, we have magnesium. Again, that one's a metal on its own. So magnesium as a pure element is just Mg. Nitric acid. Now, anytime you see acids in your equations or in any of the practice, there's a table on the back of your periodic tables that has the list of common acids on it. It's also on page 37 of your notes. So there's a copy of that table there in case you are looking for it and can't find it anywhere else. But nitric acid is HNO3, and you'll learn more about naming different types of acids in grade 11. Then we're making hydrogen gas. So hydrogen gas is a diatomic gas. It's part of the Hofbrinkel group, gets that little 2. Magnesium nitrate is an ionic compound. We've got magnesium as Mg2+. Nitrate is a polyatomic ion, NO3-. We crisscross, and that is going to give us MgNO3 2. So now we write out the skeleton equation. Magnesium plus nitric acid gives hydrogen gas and magnesium nitrate. Now we need to balance it. Magnesium and magnesium, 1 of each. Hydrogen, there's 1 on this side, but there's 2 on this side. So we need 2 hydrogens. Nitrate as a group, there's now 2 of those here and 2 of them here. So now it's balanced. The type of reaction for this one, we have a single element and a compound where the magnesium and the hydrogen are going to swap places. So this is a single displacement reaction. So now you've got some practice questions to do. Page 36, go through and do those for practice, and the answers are posted in the answers folder in Edsby so that you can go in and check all of your work for that page. But then for page 37, there's a few more practice questions, and this one's going to be a submission for a homework check. So the answers to page 37 are not posted. You're going to give them a try and then submit it to me, and I will give you some feedback. On pages 38 and 39, you're going to find some extra practice. So we're coming to the end of the chemistry unit. We only have one topic left after this, and that's acids and bases. So this is just a bit of extra practice that's optional if you would like to do it or not. The answers to both pages 36 and 38 and 39 are posted in the answers folder in Edsby, so you can check them if you choose to do them, but you don't have to submit them.